Hello, I'm Aggelos Kiayias. I'm Chair in Cybersecurity and Privacy at the University of Edinburgh and Chief Scientist at Input Output. In this presentation, I'm going to be talking about scaling blockchain protocols. So let's start with what is scaling when we talk about blockchain protocols. So to understand the problem, it's helpful to think of a blockchain protocol with the metaphor of a pipe. The blockchain is the pipe, and you have transactions that are coming in at the top, and then they exit in serialized form. To understand the problem of scaling, think of the pipe and the width of the pipe being the throughput of the blockchain protocol. So the wider is this pipe, the more transactions can be filled in simultaneously. At the same time, the length of the pipe is the time it takes for the protocol to serialize them. So that's the settlement time. So ideally what we want from a blockchain protocol is to have wide throughput, so the width of the pipe is as large as we can make it, and then the length of the pipe is as short as we can, so that it settles transactions as fast as possible. And the challenge is that we would like to achieve all that while maintaining a number of other properties that are essential for this class of protocols. And now, what are these properties is that what you see here in this slide. So first of all, we have that participation should be dynamic. This means that parties can engage with the protocol at the time of their own choosing, and then they may depart from the protocol, also without announcing themselves. So we call this dynamic participation. Furthermore, and connected to that, is the property of the protocol being able to self-heal. This means that when there is certain extreme conditions that happen in the network, for example, you have a large number of nodes that may suddenly go offline, the protocol should have the ability to recover from whatever adverse conditions like may be created by the absence, let's say, of a large number of nodes. Now, the next property is that we have to have resilience to faults. So this means that the protocol should not only be capable of withstanding nodes departing and arriving, but it should also be capable of withstanding nodes deviating from the correct protocol execution. This means that we cannot rely on every node having the correct version of the software. Blockchain protocols are written as open source software, and thus someone, in principle, if they wish to do so, they can tinker and modify the code. So the protocol should still be able to operate correctly and be resilient to faults as long as this number of faults are not becoming, let's say, the dominant majority or the majority of the nodes that are running the network. The third property is about incentive alignment. The nodes that execute the protocol, they do that out of their own self-interest. So it must be the case that the protocol creates the right set of conditions for rational participants to want to engage with the protocol, to operate according to the set of rules that the protocol sets with its software. The fourth aspect I have here is called inclusiveness. And this is a very critical property because we want these blockchain protocols to become a global infrastructure. That's how we think of them. We think of them as having the ability to serve a multiple different type of applications and systems that they can use them as basic foundation for doing other things, applications that users want. So a blockchain protocol should not create a monoculture of a system that somehow it serves only one particular purpose or is good only for one particular purpose, and then it's unsuited for something else. And finally, the protocol, we want to create an environment that we call predictable. And this has two different facets. One has to do with the service that it provides. So the service should be predictable. Just to give you an example of what service might mean is like, how long do you have to wait for a particular transaction to get settled? Now, observe that here predictability doesn't mean that it has to happen fast necessarily, but it means that you have to know how much time is going to take, right? So, and knowing means you can plan for it. So it might take a certain amount of settle, but being predictable means that when you prepare to do something that requires a blockchain application, you know exactly how long is it going to take, and you can plan for this accordingly. And in terms of the service you receive is one aspect, but one other aspect of predictability is also the cost of the service. In these systems, accessing them requires paying transaction fees, for instance, and the price for the service you get in the future is also another aspect that must be predictable. So this is the challenge of scaling blockchain protocols. You would like to get this metaphorical pipe as wide as possible so that you can get as much throughput, as many transactions as possible into the protocol. You want to be as short as possible so that they settle fast while maintaining all the properties that we have here. So let's focus first on how do we maximize the bandwidth utilization. So get as much throughput as we can from the network. So to understand this question, let's consider a network that has a certain capacity. And by capacity here, we go back to this metaphor with the pipe. The question is, what's the width of the pipes that connect the nodes? Ideally, we would like to use as much as possible of that capacity with the blockchain protocol. But the question is, as the blockchain protocol has a lot of things to do, is it capable of using almost all of it or nearly all of it? So that's the question we want to explore. So what can we expect in terms of capacity from a network that connects multiple nodes and delivers everyone's inputs to everyone? So it's easy to see that the capacity of a bilateral link will be the highest throughput that we can hope for. And now you can ask, like, is it possible to reach that capacity while delivering everybody's inputs to everyone? Especially when you are in a situation that you have high congestions, right? So there's a lot of information that you want to communicate. And that's possible to do in gossip networks. And just to give you an idea why, you can think of this simple example of a ring where we can calibrate the rate of data that are pumped into the network by each node. And now you can think of it simultaneously. So we can set it to the right fraction so that if then this is propagated along the ring, it will give us exactly the maximum capacity that we can achieve. Now, that's a simple example, but the same effect can also be achieved in a gossip network, which connects multiple nodes together in the way that the blockchain protocol does. So, given this, the trouble with throughput in the context of blockchain protocols is whether the blockchain protocol, now that you can think of it sitting on top of this gossiping network, is it capable of using as much of the network capacity as possible? So ideally, we would like to use it all. Like we would like to use all the intrinsic capacity of the underlying gossip network. And the difficulty is that the blockchain protocol does not merely want to propagate information across the network from all the nodes to all the other nodes. What it wants to do is also enable the nodes to reach agreement about the information that has been shared. And the challenge about agreement is that we would like the nodes to reach agreement despite the fact that some of the nodes might deviate from the protocol that they're given to run. So they might have, let's say, modified the software. So let's see some of the existing standard approaches that are used in the context of blockchain protocols and how do they fare with respect to utilizing the throughput. So one example here is what you might call a BFT-style protocol, where there is a leader rotating across different nodes that collects a number of transactions, packages them in a block, and then propagates that block to the network, while the other nodes now can take further action on it. For example, like they can vote on it and they can help each other reach agreement about what was communicated. Now, if you want to understand how much of the capacity we use, it's helpful to lay out a little bit of equations here. And now let me just say, to explain what you see in this slide, we have the fundamental limitation here is going to come from this inequality that you see here at the top. So this basically says that the rate that blocks are generated cannot be too high. So there is an upper bound on the rate of that blocks are generated. So if f, this f value here is the blocks per second that we can get from the network, and capital delta is the network delay in seconds, so it holds that f times capital delta should be less than 1. Why is that the case? The reason here is that we would like the information of a block to propagate to the whole network, so that by the time the next block is generated, whoever generates the next block has seen the information from the previous block and has updated its local state. So let's see now, what does it mean for throughput? And if we say throughput is this quantity that you see here, C, which is bytes per second, then it is very easy to see that this gives us a lower bound on the delay capital delta. That's because B over C would be the time it takes to push one block through a single link, where B is the bytes we get for each block. And then this has to be multiplied by this little delta, which is the diameter of the network. And that's because the block has to be pushed through across the whole network, right? So the diameter of the network here is important. And just to remind here that the diameter is like the length of the path that connects every node to every other node, let's say the minimum path. So now if you put all that together, it's very easy with just a little bit of calculation to see that in this BFT style approach, the throughput we're going to get is C over a little delta. And now that's a little bit unfortunate, right? Because already this shows that you cannot get very close to this capital C, right? Capital C is what we want to approximate. We want to get close to that in terms of throughput, but now we are just on a fraction of this. Some of you that are more familiar with Nakamoto style now won't be surprised that the situation becomes even a little bit worse for the case of Nakamoto style protocols. And that's because in the case of Nakamoto, we need actually this block production rate to be even a bit less. And this is what you see actually from the second inequality here. So this f parameter actually not only has to be smaller than 1 over delta that we had here, but has to be a bit less, where here PA and PH are corresponding to the probability of success of the adversary. This is the adversarial Byzantine nodes that we were talking about, and pH is the probability of success of getting a block for the honest parties. So this F, this block rate, has to be even less than 1 over delta than this 1 over PA minus 1 over pH expression. And this is actually a property that we have proven tight. And thus, the result here is that the throughput becomes even less, right? So it's even less than this delta fraction that we were getting in the BFT style. So this means, and just now the takeaway from this, is that running blockchain protocols, those that enable you to agree on this serialized output, has a penalty for throughput. So how to solve the problem with throughput? There's two ideas that are fundamental to the solution that I'll share with you in the next few slides. Payload decoupling and concurrent processing. And we will see now how with these two ideas we can put them together to address the limitation we get from the standard approach for blockchain protocols and get close to the capacity of the network. Before we go there, I want to also focus a little bit on computation, because this is an important consideration as well when you look at a blockchain protocol. The reason here is that transactions, as they flow into this metaphorical pipe we were talking about, they're not just neutral objects. The nodes that process them, they have to perform computation to validate their contents, run scripts, and ensure that the transactions are processed properly. So if you look at both the BFT style and the Nakamoto style approach in these blockchain protocols, what happens is that as the block is relayed in the network, the nodes are basically validating the computation and effectively repeating the computation. So this actually is very bad from a computational perspective if you look at it from the whole network. So if you have an amount of W, which is the work that you have to perform in every block, if everybody has to do it, this will give you a complexity of, as we say in computer science, theta n times W, which means that you have to do linear amount on the amount of work you have and linear amount in the number of nodes. Now, that's not very good. I mean, it's clear that we have to do W. There's no way to avoid the work we have to do in every block. But the question is like, do we have actually to do this n times? And in fact, there is another third fundamental idea to the protocol I'll share with you, which is called the centralizing computation, that can make it feasible to go down and bring the computation to k over w, where k now is a parameter that doesn't have to depend linearly on the number of nodes in the system, but can be much less, and even bring this down to what might be theta w, which is proportional to the amount of work that we can do. So this is the central idea of Ouroboros Lias, which is the protocol that we've been working for quite some time now, and solves exactly this problem of reaching the maximum throughput that the underlying network offers. The key idea of the protocol is that first, it uses this idea of payload decoupling. A simple way to understand payload decoupling is to think that you have here a consensus protocol, and you can think of this as a regular blockchain where you get these blocks that now normally would contain transactions, but in the case of payload decoupling, and that's now the key idea, they contain references to the payloads, which are the transactions, right? So this is, if you want, like a blockchain of references. And the nice thing about this is that these references, as it's clear that it's possible to do, they don't have to be as big as the objects that they refer to. So the objects can be very large. Nevertheless, the references themselves can be very short. For example, can be at the level of a hash or a hash in a number of signatures. So the observation now here is that this payload decoupling enables this blockchain to be extremely lightweight and doesn't have to contain as much information as the information that we would like the network to communicate. Then we have the actual information comes in the form of these other objects that you see here, larger on the right, that we call the input blocks. Now, these input blocks are the transaction carriers that are constructed individually by the nodes in the network. And the key aspect of that generation of these input blocks is that it can be done concurrently. So this means that you have different nodes in the network generating these input blocks without coordinating with each other. So it's like packaging a segment of work that is a candidate to be included in the blockchain and then releasing it to the network without having to coordinate with each other. Now observe that what is really nice about this approach is that it also decentralizes computation. The centralizing computation here, remember from the previous slide, is the ability of the protocol to have different nodes perform computation that can be shared with others without imposing the same task to be done to other nodes. How do we achieve that? So a key point is that we use this technique that we call stake-based endorsing, which, just to visualize it in a simple way, it's like electing a small committee from the set of all nodes in the system to look at the processed information, validate it, and then certify it by issuing a signature. And then by using a concept that we call stake-based multi-signatures, it is possible to get all those signatures together and compact them in a succinct certificate that can now accompany the input block. In this way, we have decentralized the computation and we have enabled concurrent processing while enabling an underlying blockchain protocol, let's say here you can think of it as a Nakamoto-style protocol, to order this information without having to worry about how large it is, because it only uses references that are certified to be correct. So that's the central idea of the LEOS protocol. So if you were thinking about concurrent processing, as I presented it in the previous slide, you would have noticed that this means that nodes perform this processing without coordinating with each other. So the natural question is that there might be conflicts in the way that they view things. So we have to reconcile. And this is the challenge which is associated with concurrent transaction processing. And it's illustrated here in this graph. You have two ledger states, presumably owned by two different nodes. This comes with transaction outputs and transactions which are processed with respect to that ledger state. They are different because these are two different nodes. And now the protocol that takes this approach, it has to reconcile those and put them together in a single package and create a coherent ledger state. So there is a very interesting distinction here about how this works with respect to the account model and what is called the extended UTXO model, which is used by blockchains like Cardano. So the account-based model, the problem that has to be solved for concurrent processing is the merging of this state, which you can see it here on the left. So basically what happens is that you have, let's say, the original state of the ledger, let's call it S. Then we have some transaction 1 that leads to a state S1, another transaction 2 that leads to state S2, and now these two are computed independently. And the problem that you have to solve is that you have to now take all this information and merge it together. Now, in the worst case, this can mean that you have to repeat some of that computation, and this is a bad thing, because you remember about what we said about decentralizing computation. It means that we would like to do the computation on the left, we would like to do the computation on the right, and then have a way to put that together without having to redo things like pay more. So the extended UTXO model is exactly the tool that enables us to do so. And to see this with an illustration, you can see here on the other side of that slide. Because in the extended UTXO model, you can think of the transactions as being organized as a graph, and every output is basically like a triple, like it has some script, it has a value, it has some data. So, and this can be decided independently. So if you spend an output, you just present some value. This is called like the redeemer string, that if it is accepted by the string, then the output is spent. Now, if it happens that you have conflicts, now that's very easy to see if you look at this from a graph theoretic perspective. And you can see here in the example that we have on that slide, you have a bunch of transactions. Two of them were generated on the left, another two on the right independently, and it so happens that one of them is using the same input, which is this blue node there. So it's very easy to detect that. Very easy to detect the inconsistency. You don't have to redo the computation, and the only thing you have to do is like trim out one of them according to some standard serialization rule, and then you have immediately the merged state. So this is how the extended UTXO model gives us a lot of power in implementing this concurrent transaction processing very efficiently. Let's come now to the topic of settlement, which, as you remember now, this is from our metaphor at the beginning, like this is how short we can make the pipe. The protocol has to settle fast. Consider a network that has a delay capital delta, and the question is, what is the inherent settlement overhead that blockchain protocol will have? Right? How fast can we make it? So the trouble with settlement is that in both cases of Nakamoto style and BFT style protocols, the underlying blockchain protocol has to perform a number of steps and exchange information so that the nodes that are communicating with each other, they can ensure that the information is correct and everybody has agreed. And there is overhead that comes with that. Now, in the case of Nakamoto-style protocol, because of this inherent limitation we have with adversarial parties, which is a fundamental property of this protocol, the amount of time that we have to wait comes with a penalty, which is a product of at least the delay of the network times this parameter, log 1 over epsilon, where epsilon here is the consistency error. So this means that you may have to wait a large number of network delays for the network to synchronize. And intuitively, in Nakamoto-style protocols, this means that you have to wait for a number of blocks to be communicated and added on the blockchain in order for you to have assurance that the transactions have settled. In the BFT-style setting, the situation is better, as we can get expected constant overhead. So that's what we mean by this theta delta. But the complications of BFT style is that they make it harder to get dynamic availability, which is the property, as we said, that nodes come and go. And even if that's possible, it becomes unclear how is the protocol capable of self-healing. The reason for that is that in BFT-style protocols, you have this voting, and this voting finalizes a state. So the protocol inherently doesn't have a way of revisiting state in the case of extreme conditions, which is one of the fundamental properties of Nakamoto-style protocols. So how to solve this? And the approach you can think here is a best of both worlds approach. So is it possible, let's say, to marry here the Nakamoto-style ability of self-healing with the fast ability of BFT-style protocols to settle. This is the approach that we have in the protocol that we call Ouroboros Peras, and the central idea of the protocol is that, as you can see here on the right of the slide, we have a main chain that you can think of it as for instance, a Nakamoto-style proof-of-stake chain like we have on Cardano with the Ouroboros protocol. But now, in addition to that, there is a layer of stake-based voting that generates the opinion of the network fast exchanged between the nodes about which way the blockchain is going, if you want to think about it like this. So the key point of these votes is that they contribute to the weight of the chain. And now, using them, what we show in the analysis of this protocol is that it is possible to get this weight and influence the chain selection rule so that the underlying blockchain can settle much faster. And what is nice about this is that we don't lose the ability of the underlying protocol to self-heal. Now, observe that at least in the most simple implementation of this, the protocol will be able to generate those votes above a threshold under, let's say, normal operation. And then if you don't have enough participation, you may want to do other things. For example, a simple thing that we show you can do is that the protocol can revert to a cooldown period where it's just operating in sort of a slow mode that settle transactions like in the original Nakamoto style, until participation in the network builds up again. So now let's come to this an important point about the uniformity of the nodes that has to be addressed, because the way we were thinking about this protocol so far is that all nodes being the same. But if a node has an extremely low throughput, we don't want that node to be the choking point of the network. And in fact, it makes a lot of sense that in the periphery of this network, we have a lot of really limited nodes. For example, you can have cell phones, you can have like devices with limited throughput. So the question is, how do you accommodate that? You don't want to slow down the whole network just for that. And this is the question that has to do with what's known in the blockchain literature as the light client problem. And just to give you some of the approaches here, going back to the original work of Nakamoto, we have what we call SPV clients, which they give you a good level of security, and I call them trustless in quotes, because of course trust is a very nuanced topic, but they give you a reasonable level of security. You don't have to trust anybody in particular with an SPV client, but they're inefficient because you still have to download the headers that come with the blockchain. On the other hand, you can have these centralized API providers that are used very widely right now in a lot of blockchain networks, The performance of those is very good because you can get the information you need about the blockchain directly by talking to them. They are efficient, but of course the issue is that they are centralized. So on the one side, we have this complexity which is linear in M, which is M is the length of the blockchain. On the other case, we have constant, but it's centralized. So this is something that needs to be solved. And the solution here comes with combining two tools, the stake-based multi-signatures, which I mentioned before, and some tools that are called proofs of proof of work or proofs of proof of stake. And of course, the proofs of proof of work, PAPAUs, these are something that of course applies to proof of work-based blockchains like Bitcoin, whereas proof of stake applies to proof of stake blockchains, like, for example, the Ouroboros and Ouroboros-based blockchain like Cardano. So what's a proof of stake? Intuitively, it's a protocol that a client can run, a light client can run, which might be a wallet or a dApp developer that's launching an application. So it interacts with what we call this light client API, which is a protocol that is trustless, again, in the sense that you don't have to rely on any specific node, so you can get security at the same level as the underlying blockchain, but the communication that you have to pay is logarithmic on the size of the blockchain. Let's put now everything together and see what we get. So here is the Ouroboros protocol that you can see here in the middle on this chain, that we combine it with these two new protocols, or you can think of them as overlays, Leos and Peras. And at the same time, with light client support. So what you get on the right is the Leos overlay that fills up all the available throughput of the underlying network. And on the left is the Peras overlay that uses stake-based voting to enable the protocol to settle fast. And at the same time, here at the bottom left, we have a proof of stake that enables this light client API. So light clients will be able to connect with the network despite the fact that they may have limited throughput. Let's focus next on incentive alignment. This refers to the ability of the protocol to organize all the nodes that are rational, and as we call sometimes in game theory, they are like utility maximizers. They align their interests so that they engage and the correct protocol behavior emerges out of their self-interested participation. If you think about it in this sort of high-level picture, we have one ledger state is then preceded by a next ledger state because the maintainers contribute to the protocol. And by contributing to the protocol, they spend resources. And the key question here is that in order for incentives to be aligned, they have to be motivated to do so, which means they have to be rewarded. And there are three main ways that this can be done in blockchain systems. So we can increase the token supply. So we can mint new tokens, so the system can mint new tokens so that they are distributed to those maintainers, which later they can sell, for instance, to offset their costs. We can take the transaction fees from the transactions and give it to them. That's the second approach. And finally, the third approach is to reduce overall the token supply so that the holdings of those that are engaged in the network, they become more in relation, and so they're motivated to process more and more transactions so that they achieve that. And of course, this would make a lot of sense in a proof-of-stake setting. So these are the three techniques, and now I want to explain how is it possible to measure maintainer performance, because this is something that enables rewards and incentive alignment to be done in a fine-grained way. So as maintainers, the nodes engaged in the network, they, if you want, leave a footprint that creates indicators in the consensus ledger about how much they have contributed to the protocol. So the key feature of a protocol that can do fine-grained reward allocation is its ability to measure precisely how much everyone has contributed without allowing nodes to game this metric. So in other words, if I contributed an amount of X to the protocol, that meant I have to pay a certain amount of resources for that. This is accurately reflected in the emerging ledger. And just to give an example here, in the case of Ouroboros browse, the main chain blocks that are included is the main indicator that every maintainer gets. So these maintainers are called stateful operators or SPOs, and we measure their performance by seeing how many blocks they've contributed versus the expected number. Now, what is really interesting about the approach that I just presented to you by combining this overlay of Peras and Leos is that this gives us much more opportunities to measure in a fine-grained way how maintainers participate in the protocol, something that results in a lower variance for the rewards. So in summary, Ouroboros Leos with Peras overlaying, it gives all these properties that we started with, or we had like a set about a layer 1. Specifically, it's a permissionless proof-of-stake protocol that has dynamic availability and self-healing. It gives you fast settlement, max throughput, and a fine-grained reward allocation. So our next step is to look at, is it possible to go beyond max throughput? Now, this may sound as a paradox in itself, but it has to do with revisiting one of the key requirements that we set at the beginning of our analysis, which is that full nodes manage the whole ledger. So what happens if we just drop that? And then we allow only a partial view of what's going on to some of the nodes that participate in the protocol. And there's two main approaches here that are being followed. The sharding approach that you see on the left, which you can think of it as a collection of multiple pipes that organize the transactions separately, and then the maintainers are assigned or given responsibility for some of them partially, while different transactions are routed to their respective pipes. One of the challenges here is that you still want this whole thing to act as a single ledger, so you may have to do cross-shard transactions if the need arises for interaction between transactions that are in different parts of the ledger. Now, this is something, let's say, that happens at the layer 1 level, but a different approach is the layer 2 so-called approach, where you have the ledger as a foundation. You maintain it at its maximum throughput that you can get so that everybody gets the same information. But then you have individual applications that are built on top of it that can achieve much higher throughput as they can use specific network configurations that are suitable for the particular application that is implemented in each case. And then what happens is that when things go wrong there is a way to fall back on the main chain protocol and then resolve any disputes that the parties may have by going in the protocol and posting the right set of transactions. So you can think of the operation here of the protocol as operating in an optimistic mode. When everything is fine, you don't have to touch the main chain, and then you can enjoy really high throughput for a specialized use case. And then when things are not going well and there is disputes, disagreement, or problems between the parties that are implementing this specialized protocol, the parties can fall back in the main chain and resolve these disputes at that level. The layer 2 approach is the one that we will focus on for scaling beyond the max throughput. So to understand layer 2, a simple example is a payment network that you can understand simply from this picture. So a payment channel is the fundamental component of a payment network and is a two-party protocol. The two parties, the black and the red that you see here on this slide, they agree on a certain amount of information, on a certain capacity of this payment channel, and then they can issue multi-signatures, signatures that are signed by both of them, on the amount of coins that among the 10, or splitting this amount of 10 coins between them in some arbitrary way. What is nice about this is that the parties can rapidly exchange this information without involving the main chain at all. Moreover, if there is a problem, if, let's say, one of the parties does not cooperate, the main chain is suitably programmed so that each one of them individually can take their joint state and settle it back so that they can correct any issue by assigning the split, the latest split that they have in their bilateral interaction. You might observe that there are issues here that have to be dealt with. For example, like what happens when one of the parties deals a replay and replays an old state to the main chain, but the protocol is specially designed to address this problem. So this is the fundamental object of a payment channel, and by combining multiple of those channels together, you get a payment network. So this is behind the protocol that we call Hydra, and generalizes this idea to what we call a state isomorphic channel. So what is a state isomorphic channel? Is first of all, not just payment, but arbitrary smart contract computation that is isomorphic to the smart contract programming language that is used in the underlying blockchain. So the idea is very similar to a payment channel. You again have the state of the channel being maintained by as many nodes as you wish, that unilaterally they update it and then they communicate it to each other, and then using multi-signatures they just combine it. And it's possible with using similar techniques to these state channels to have this very fast operation of smart contracts between a set number of parties that wish to advance them as soon as possible. The head protocol is the one side of the layer 2 suite of protocols that we call Hydra. Hydra tail is the other side, which deals with a different configuration between the nodes that want to engage in layer 2. While the Hydra head has a number of nodes exchanging information all together and advancing a state of the underlying blockchain as fast as they can, in the Hydra tail setting, we have a single server doing that with multiple nodes submitting transactions to it. The key issue here is that the transactions that are coming from different clients are given to the server, and then the server processes them very fast and regularly posts updates of the state that is carved out away from the protocol back to the main chain. Again, we desire here to have an isomorphic situation, so whatever applications are running on top of the server will be of the same kind that can be executed in the main chain. With the difference, of course, that these are operated here and acted off-chain, while the main chain is actually receiving just the summary of that execution. Of course, you might ask, how can we trust the server to do the right thing and give you a correct update of the state that is on the main chain? And for this, the protocol relies on what is called a snark, which is a type of protocol, a succinct non-interactive argument of knowledge, as it's known in cryptography, that enables to do a very short proof that the transition of the state happens correctly. The Hydra protocol suite, aside of the head and the tail protocol, has a number of other supporting protocols, like the interhead and the tail protocol is a protocol that connects multiple heads and tail instances together, facilitating the creation of the network. So this means that it's possible to transfer state from one instance of such an off-chain protocol to another without having to go through the main chain. And then network rebalancing has to do with maintenance across this network, especially if you have imbalances that require to modify the state, and you can think of it as a sort of a bookkeeping information for the whole network. And finally, because everything is off-chain and might be hidden, it is desirable to have special auditing protocols that enable external third parties that might not be active in these layer 2 operations to have some information about what's going on this off-chain network. So this here wraps up the layer 2 approach of Hydra that shows how you can go well beyond the max throughput by using these specialized applications, blockchain applications that are living off the main chain, but still, in every case, they utilize the same scripting, the same type of programming with the main chain. A different way for obtaining a layer 2 operation is to have an actual other blockchain work in parallel to the main chain. And this is what we call the partner chain approach. Here you can think of blockchains as being siblings, that you have one that is called the parent that lends its security to a child blockchain that can grow and then become a equal partner or an independent or even an independent system. So this is fundamentally relies on a concept that we call merge staking, which means in a nutshell that it is possible to use the stake that you have in the mother blockchain to create blocks and maintain the partner chain or the sibling chain. And this is also what's illustrated in this simplified diagram. You have these red and black nodes, which are operators of the main chain that now lend their stake without having any fear of losing it to maintain these partner chains that are then connected to the main chain. Some of the features of the partner chain approach is that the token distribution and initial minting can happen on the main chain. So each one of these partner chains, they can have their own tokens, but they can actually mint them and distribute them on the main chain while giving rewards in each individual sibling chain. And then using a trustless bridge between them, it is possible to facilitate transfers between those different blockchains. So let's talk about transaction fees now. Issuing transactions on the blockchain needs to come with some overhead for various reasons. The simplest one to understand is that you cannot just allow you to spam the network. So there has to be some resources which are tied up with every transaction that is issued. Furthermore, a transaction itself is a unit of work which is proposed for processing to the network. So it makes sense that it carries a cost, and then that cost can also be a payment that can be used to be distributed to the nodes that are maintaining the network. So there's two fundamental approaches that have been developed in the blockchain industry. The first one, which is the one that has been studied quite a lot, is the one of Bitcoin, which follows a first price auction approach. The idea is that you can attach as much funds you want in a transaction to be processed, and then the miner that processes your transaction can claim that as part of their rewards. The feature of this mechanism is that the prices would go up during times that the network is congested, and the benefit of this is that as prices go up, the service can still be fast, because if you are willing to pay for good service, you're going to adjust the fee that you have with every transaction to match the current demand that you see on the network. The downside, of course, which is highlighted here, is that it could be the case that a single use case dominates the prices, and the prices in the future would be unpredictable. Furthermore, given that this is an auction mechanism, it completely depends on user behavior. So the prices will not automatically go down when there is no congestion. Right? The users will have to bring them down. The Ethereum approach, on the other hand, which has evolved over a period of time, is to adjust dynamically the price of transactions. So you can think of it as mostly like what is sometimes called like a post-it price mechanism. The price will go up during congestion time. So this will, again, for those that are willing to pay high, this can bound the delay. But then it's still possible for just this one or two use cases to drive prices up. On the plus side, compared to what Bitcoin was doing, we don't rely on the user's behavior to drop the prices will drop automatically. So an important question here is whether these approaches are matching everything we want to do. And it's nice to juxtapose them with what Cardano is doing today. Cardano follows this flat pricing approach, which has this very nice feature of having the prices being predictable. But on the downside, this means that when the system is congested, then there's no way to bound the delay. So if we want to highlight what are the desired properties of transaction fees, we want on the one side to accommodate diversity and inclusivity. And what do we mean by this? Is that it shouldn't be the case that one use case drives the prices up, because that's possible. If that's the case, it could be possible to stifle every other use case that doesn't make sense to follow the same transaction pattern, right? So the whole system can become a monoculture, which is something we want to avoid. Furthermore, the second important aspect is that we would like predictability for both prices and delays. So this enables nodes to plan ahead in the future. So it should be possible if I'm organizing what I'm going to do with the blockchain now. If I look, let's say, a month ahead, I'm able to predict what would be the cost of my system for engaging to the blockchain. So, and I have to say, of course, if the system is not congested, that's not a problem, but we would like this to be the case despite the system can come under congestion. So this brings me to our first approach for addressing these questions, which we call tiered pricing. So what tiered pricing does is that it divides the capacity of the underlying consensus protocol into different tiers. Every tier gives a differentiated service according to some rule and has its own individual pricing. The system continuously adjusts the tier number, the size, and pricing to match demand. So if you want, what the system does is like it actively searches the best configuration that it can tier itself to match the demand that it has in terms of transactions submitted to clients. What is the advantage of this tiered pricing approach compared to the other approaches, all the other approaches I showed you earlier, is that we can accommodate a diversity of applications with significantly lower prices for those transactions that desire the lower level of service. At the same time, and that's what's really interesting about this does not mean that it will come with a penalty on total revenue. And that's because while some of the transactions can pay lesser fees for getting the lower degree service, the transactions that can aim for a higher degree service, they can pay more than matching basically the revenue loss that we have from the low price transactions. The second approach that comes to our portfolio of protocols for pricing, we call blockchain space futures. And the key point is that we can get predictable prices despite the fact that we have congestions. Now observe that with tiered pricing, because prices are dynamically adjusted, it's still the case that if you look far in the future, you won't be able to predict the price, right? Because the price will go up if there is demand. So the blockchain space future is an approach that can mitigate that problem. So the key idea is that you enter with a counterparty to an agreement that you will pay a transaction fee for the future. So you can pay it, in the simple case, you can think of it as an option to issue a transaction. Let's say, for this simple example, 4 blocks ahead. And now, in the case of Cardano, let's say you would pay this with X ADA. And then you will pay basically X plus the contract fee, that what is required, let's say, to use this service with a counterparty. And then when the time comes to exercise your option, and you do that, you will post your transaction with the fee at that time, and then in an automatic way, via the future contract, you will be reimbursed the amount that you're owed, which is Y minus X, right? Y being the cost of the transaction cost in the future point, and then X was the one originally when you entered into the futures contract. Now, of course, observe that the key requirement here is that we have these counterparties who absorb the risk, and of course they're paid for that. What was interesting about the future approach is that it works with every tier, but it also requires in every tier to have the counterparties that are needed. And it might be possible to have counterparties, let's say, for low demand of transactions, right? For a small number of transactions, there may always be a matching counterparty which is interested in providing that service. But it could be the case also that for certain tiers and for certain types of demand, it's very hard to find a matching counterparty. For this, we have a different approach, which we call blockchain space tokenization. What happens here is that we allocate a special tier, which will allocate transaction space in a different way. The space of that special tier, you can think of it as being tokenized and auctioned to those that are interested in participating at specific periods of time. You can think of it as a way of auctioning tokenized options for space. Now, what you get from such auction, if you're interested to participate, you can think of it as your option to claim blockchain space at a specific rhythm. And then there is an on-chain mechanism that defines your rhythm. We call this the token age or the space token age, which says that if you post a transaction with a particular space token that you've acquired from the auction, then there is a limit to how fast you can post your next transaction if the system is under congestion. The key advantage here is that there's no need for counterparties, as the system can actually manage this blockchain space tokenization itself, but by having this special tier for it, and the size of that tier can be adjusted based on the result of that auction. Finally, let me move on to the final piece about pricing transactions, which has to do with what we called earlier inclusiveness and diversity for a blockchain system. And it addresses the issue of smart contract enabled blockchains making it feasible for applications to issue their own tokens and having their own users, which creates the problem that those users may only have the token of the application and may not, in other words, have the native token that they need to use in order to participate in the pricing mechanisms that I just described before, which, as you noticed, they were all required to use the base system token to engage with. So the bubble fees construction is an approach that enables those that issue tokens and distribute them to users, different token holders, to issue transactions which are a segment of a full transaction that facilitate a swap of the underlying application token with the ADA or the base token that is needed to complete the transaction. So now the network that diffuses transaction also facilitates a market of transaction fees where application clients, they make offers on the tokens that are used by the applications, and then you have other interested counterparties, which could be, for example, blockchain maintainers, that match those offers, and they swap the underlying tokens of the application with the amount of basic token that is needed to complete the transaction. So that's why, as you see there, the transaction becomes like a puzzle that comes together, and then at the end, if the swap happens, the right amount of base token that is illustrated here with A is matched and is given to the whole transaction so that it settles in the blockchain protocol, while the counterparty that matches it receives the application token that supposedly have value for it. Putting all this together, this brings me to the conclusions, and I think like the main taking point from all this scaling overview is that permissionless blockchain protocols has come a long way and can go a long way in terms of how good they can scale. So just putting everything I told you together, here is the basic construction with all the additional features, seeing now what you have here as the Nakamoto style protocol, which for the case of Cardano would be like the Ouroboros protocol. So this is, let's say, the classical blockchain. And now you can see how this is enhanced with, on the one side, the Peras overlay, which enables fast settlement, here on the left. On the other side, here on the middle, we have the Leos overlay that enables to maximize the bandwidth that is available to the network. And then we can even go beyond that maximum throughput by utilizing these layer 2 approaches that enable the system to scale and facilitate different types of pricing for different types of applications that give the underlying system diversity and inclusiveness. Finally, really lightweight nodes that want to interact with the layer 1 blockchain can still do that by using the Light Client API. So this puts everything together and shows how is it possible to build a blockchain system that indeed scales at the level that you might hope a system like that would scale, going well beyond what originally was thought that blockchain systems can achieve. So this brings me to the end of this presentation. Thank you very much for watching Scaling Blockchain Protocols.